All right, we're recording. Welcome to Monday. So let's start by looking at what we're doing over the next few weeks. Then what we're looking at this week. Then I've got, here. Right. Then pretty soon I've got lined up for you guys what homework I have for you guys coming up here pretty soon. Right. And then a starter question that's going to lead into what we're doing today. Right. So one thing at a time here. You guys know that we have a 4-day week this week, right? Right. We're going to be here on Friday. Right. So between that and they've got two topics that are actually kind of related to each other that I think I can put together and save a couple of days. Here's what we're looking at next. Actually, I should reverse these. I should say harmonic motion and waves. AP's units for these are Unit 6 for harmonic motion and Unit 10 for waves. Okay, so but we're just going to do these together. I think I can get all this in by next Wednesday, I think, and then we can take next Thursday and Friday and start on electricity, which is AP Units 8 and 9, and that'll be our last topic. Okay? So that'll take at least until April 16th. If we keep a really good pace, then we get finished by then. We might go over by a couple of days, but then that'll take us into review. So hopefully get at least 1 week, maybe 2 good weeks of review in, and then your AP exam is right around the corner. You guys know your AP exam is about 5 weeks from now, right? About 5 weeks. Yeah, so that is coming up. So that's it. This week, what's going on? So I normally save labs for after I give you guys a few days of notes, but I do like this idea. I've tried to do this sometimes in the past of actually, before I give you any notes at all, just open the section with the lab. Because then we don't really know how it's going to work out. You guys don't have any really equations yet. So let's try this approach this week. Okay? So we're going to be looking at a pendulum swinging back and forth. I wonder what variables could affect how much time it takes to swing back and forth, something like that. Okay? Look at the mass, the starting angle, the length. Okay? So save notes and demos for tomorrow. We can give you guys a few at the end of class today, but this can be our main focus tomorrow. Pause right there. Let me show you guys some pages that are involved for this week. Right, so if you're in class, I just handed these out at the beginning of class, and if you're at home, then you guys have these on Google Classroom. Hopefully, I have these printed out. So Pendulum Laboratory, this one we're doing today. Okay. So, well, I did put this write-up on the back, but I changed my mind about this. I don't actually want you to do this particular write-up. So, well, you guys will see that later today. Okay. Now, there's another lab, Speed of Sound Lab. Probably going to save this for next Monday. That's, well, I'm up here. Here we go, Speed of Sound Lab. Okay. I think I will have you guys do the write-up for this, but again, it's not until next week. So, hang tight on that. You guys got that? Don't lose that paper. Okay. I've got some conceptual questions related to, let's see, vibrations and waves, and then specifically on sound. So if I find a good time, I'd like to fit in a Kahoot related to those conceptual questions. Should be pretty good questions there. Right? There's a basic page on waves questions, waves and oscillation. Right? Well, that does have some formulas here, so might get to this tomorrow if I can. This is a page that I normally give to my conceptual students that's like the hardest kind of math that they do, but this should be some of the easiest math that you guys do. Okay? I've got a couple of pages from college physics. So there's chapter 13 and chapter 14. I'll talk about these a little bit too, but you guys got those for now, and then we'll go over some of those and show you guys a few homework problems from those. Okay, right. You guys give the pages you got? Okay. So all right, let's go back to here, pick up where we're. Right, so college physics, I'm going to put those on Wednesday. Thursday, I want to go over the Unit 6 multiple choice questions, so do those by then. I'm going to give you guys a homework checklist here pretty soon too. All right. We don't have school Friday, so we'll come back on Monday, and that's when I'm planning to do the Speed of Sound Lab. And then I want to do the Unit 10 progress check questions, cover those on Tuesday, so finish those by then. And then probably say Wednesday for FRQs. So if we stick to this, then we should be finished with 2 more sections by next Wednesday. So I hope I can keep that schedule. Here's guys' homework checklist. So the Unit 6 multiple choice questions, I opened those up a few days ago. Just turn those in by Thursday morning so that we can go over those on Thursday. Okay. The next AP classroom section, I'm just skipping down to this one. Right. Unit 10, that one's also open. It's also been open for a few days. Right. Do those by, well, before next Tuesday. So you guys got just over a week here, about a week. Right. Then we'll cover those on Tuesday. Okay. And the college physics problems that I want you guys to do are just these 5 right here. I've chosen them all from chapter 13. I was going to give you guys some from chapter 14 also, but I was looking at them thinking, these are a little bit too far away from what AP wants you to know. So yeah, we're just going to do chapter 13 for homework, just these 5. Like normal, all the solutions are posted. So if you get stuck, you can check the solutions and get back on track. I'm saying due Monday, and you can always do them earlier if you want to turn them in before you take off for the weekend. Then feel free to do that. You do that. Yeah. All right. Is everybody okay with what we're doing for the next couple weeks? All right. All right. So jump into this lab then. So lab, what I want to know is that for a pendulum, right? You guys know a pendulum, right? They've got a mass on the end of a string, just swing back and forth, swing, swing, swing. Right? I wonder how these 4 variables are related to each other. So maybe if I change the mass on the string, how could that affect, let's say time period? Maybe I should relate everything to time period. That's probably a pretty good idea, right? Okay, so if I make this heavier and heavier, right? Let's do a quick hypothesis. What do you guys think for mass? Right? Now, there's 3 possibilities, and I'm going to see show of hands for you guys who are in class. Right? So one possibility is that the greater the mass, it's going to slow this system down so that it's going to take more time to swing back and forth, right? Or second possibility is maybe the opposite is true. Maybe for more mass, it's actually going to make it swing faster. So that would decrease the time period. Right? Time period is defined as to swing back and forth once, to go from here back to here. So 1 time period, 2, 3, 4, from counting the time period. Right? And the third possibility is that maybe it makes no difference at all. I mean, mass has canceled out quite a bit in this class. I wonder if it's going to cancel out in terms of this time period relationship. Let me see, show of hands. How many of you guys think that the first thing that I said is true, that as I increase this mass, it's going to take more time to swing back and forth? Who thinks that? Who thinks that's going to shorten the time period? It's going to swing back and forth faster. And who says maybe it's going to cancel out and oh, wow, I see a bunch of hands just went up. You guys said it's going to cancel out. Okay? Tell you what, that's a pretty good hypothesis. I would probably have the same hypothesis. I would think, well, I remember Galileo throwing stuff off the tower. Greater mass means that it has greater gravity force on it, but it also has greater inertia. And those 2 effects cancel out. So maybe it'll be the same thing for pendulum. We'll find out experimentally. We'll find out. Then we're going to go change the starting angle. I put theta naught here, right, the starting angle. Right. So see 3 possibilities. Right? First possibility is maybe as I widen this up, 30, 40, 50, 60 degrees from the vertical, right? That maybe it takes more time to swing back and forth. Right? Second possibility is that maybe by increasing the starting angle, it somehow takes less time. I mean, I guess that's possible, right? And third possibility is maybe it makes no difference at all, right? Maybe you have a similar hypothesis to that last relationship. Let me see show of hands for this one. How many of you guys think that as I increase the starting angle, 30, 40, 50 degrees, it's going to take more time to swing back and forth, more time, right? I see a bunch of hands there. I mean, that seems a pretty good logic, right? It has further to go, right? How many of you guys think that maybe it's super counterintuitive? Maybe by increasing this time, this angle actually takes less time to swing back and forth. Anybody think that? Anybody think less time? Okay. Does anybody think that it makes no difference at all? Ooh, I do see a few hands for that. Some of you guys are hypothesizing that actually makes no difference. Oh, yeah, Jerry?
Is this the same type of thing that you showed a while ago with the marbles at the same moment of inertia, where they would all start at different heights and meet the center at the same time?
I don't know. There might be a connection there. So Jared's saying, is this related to like if I had a maybe what different size marbles and then roll them down? Huh. I don't think so, but there might be a connection that maybe some kind of crazy connection I'm not thinking of. Okay. Let's think about this last relationship, length and time. Okay. So same three possibilities. As they make this longer, 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 what's going to happen in the time period? Okay. So show of hands. How many guys think that as I make this pendulum longer, it's going to take more time to swing back and forth? Who says that? More time. Got a few hands. Who thinks that as I make this longer, 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 it's going to swing back and forth faster, so it takes less time to swing back and forth? Okay. And who says it's going to make no difference at all? Maybe time period has nothing to do with length of the pendulum. Let's get a few hands there too. Okay, so yeah, we'll find out. Okay. Oh, you know what I forgot? Let me show you guys real fast. Top scientists for midterm. So here's your guys' top scientist list. Okay. Still got a few students who need to take it, so hold on that. But okay. Oh yeah, you guys are blocked too. You guys had the most top scientists, so yeah, good job to you guys, definitely. So there. I'd like to go over these questions eventually, but want to prioritize that we finish all these topics before the AP exam for sure, and then also, like I said, I got a couple students who still need to take that, do the makeup. Okay, so let's try this out. Oh, how's this lab going to work out? So you guys see this lab paper in front of you, right? So you got a table here. You guys got lots of graphs to graph these relationships. Okay, we've done. Oh, you know what? Reminds me, I got my attendance. I'm gonna grab attendance real fast. Sorry about that, guys. Good. Yeah, take a look at that lab page while I'm grabbing the attendance and digest that information. Make sure you're able to make sense of that. Oh, the midterm? I did a square root curve. So if you take your grade as a decimal and square root it, then get your reported grade. So there you go. So square root curve. Okay, I think we're missing Christina, it looks like. I think that's the only absence. Yeah. All right. We are ready to go in the lab. Okay, go. Now, you guys know, probably have an idea how we're going to do this based on how we've done past labs, which is, see, if we're relating 4 variables to each other, there's, yeah, like 4 variables. You guys know that we're going to probably control 2 of these and treat one of these as independent and treat another as dependent. Maybe we're going to relate everything to the time period. Let's do time period as dependent, right? That makes sense, right? So you might think, well, maybe I should actually have like 3 tables, right, for 3 different variables, right? Actually, don't keep track of the data for the first set. You'll see why by the end, like what we're doing with this, okay? But I'll keep track of it though. Okay? So let's see. The first one we're testing is different masses, right? So don't write anything yet. So nobody's writing anything, right? Just me. I'm the only one who's writing right now. Okay, so I'm gonna go. Okay, remember what I was gonna do? I'm gonna use these right here. Right. So nobody's writing anything yet except for me. First one we're doing is treat this guy as independent variable. We're going to control the starting angle, control the length of the pendulum, and then, ooh, I have time sub 10 and time sub 1. So I'm going to count how much time does it take to swing back and forth 10 times, and then we'll divide that by 10. And you guys know we're doing that to divide out the error, right? The error will also be divided by 10. Okay. Oh, speaking of time, who wants stopwatch duties? Who wants to run the stopwatch today? Volunteer for stopwatch. Morgan. All right, thank you. So I'm going to go with 100 grams. Okay, I'm going to, whoops, going to change this out. Okay, we'll do 200, 500, 1,000. I guess we'll have to go the other way. So let's go 50, 20, and 10, something like that. The starting angle, I'm going to have this at 30 degrees from the vertical. And since this is a control variable, remember, you only want to change one thing at a time, and we're changing up the mass. Okay, so that'll be the same all the way down. Okay. The length will be the same all the way down, but I need to measure that, and I'm about to do that pretty soon. So turn the camera. So if you guys online. You guys see this pendulum set up? Bring it up. Okay, so great. There you go. It's a pendulum, right? Okay. There's right. So there is 0 degrees from the vertical. Right. As I pull this back, there could be about 30 degrees, about 60, and then 90 degrees from the vertical would be like horizontal, right? Like that. Right. What's the length of this thing? So I need to go from the center mass of this up to the point that's swinging from. Okay. I'm saying that the string is approximately massless compared to this weight at the bottom, which is pretty close to true. This looks like 58 centimeters. Okay, 58 centimeters. So your length is 58 centimeters, right? I'm going to pull this back to 30 degrees from the vertical, which is, let's see, right there. Okay, Morgan, ready with the stopwatch?
Are we doing 10 full revolutions like back and forth?
Yeah. So I'll count to 10. I'll go 0, 1, 2, 3, and then when I go up to 10, the stopwatch, and we'll see how much time did that take. Okay. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.03.
It took, let's see, 15.03 seconds. Okay, so get rid of 100 grams. Let's go with 200 grams. Ooh, so we're doubling the mass. Okay. Pull us back to 30 degrees. All right, ready? Okay, and go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Why did we start at 0?
Yeah.
Oh, did I? I'm sorry.
Revolution, you said 0 for 1.
Okay. All right, we sorry about that. It's a Monday, that's why. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.13.
15.13. Now, some other things you might need to think about too is, I wonder if this angle is still 30 degrees. Let me check. No, it's closer to 20 right now. So it is losing some angle as it's going along. That makes sense. Maybe some frictional losses. It's losing some energy in the system. Let's keep that in the back of your mind. It may or may not be important, but keep track of it if you're doing really good science, right? So that 30 degree angle is not 30 the entire swing. Right? All right, so we're up to 500 grams right now. Get ready for 500 grams? All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.37.
15.37. All right. Yeah, it's lost a few degrees again. 15.37. Okay. Something else to consider. Was make a few simplifying assumptions, but it's good to keep track of, what are we simplifying exactly? Okay. Remember how we're saying we're keeping the length constant? Okay. Notice that as I change out the masses, aren't these weights like physically larger? They are, aren't they? See how this is the one we started with. Guys, if I hang these two, do you think that the center of mass of this one that's on here right now is lower than the center mass, the one we started with? Sure would be. So let's see. The length of this is actually not quite 58 anymore. Right now it's reading closer to 60. So maybe I'll actually record that. It's not exactly controlled. It's just pretty close to controlled. I guess if I was super strict about it, I would go through, make sure it was also 58, but it's pretty close to 58, but not exactly. Let's bump this up to 1,000 grams. Ooh, 1 kilogram. We're going to link this thing. I mean, I'll leave it like it is, but it's technically 61 centimeters. So not exactly controlled, but pretty close. Okay. So from 30 degrees, okay, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.43.
All right. And right now, by the way, it's swinging at about 10 degrees from the vertical. Okay, so 15.43. Okay. Oh, another thing too, guys, if you were doing this like as a write-up for AP, what you say to do is 3 times and take an average, right? Okay, so you would say to do that, do 3 times and take an average. Yeah. Of course, save a little bit of time today because this lab has many parts. Okay. All right, so number one, smaller. So I've got 50 grams on here, 50 grams. The length of this thing should be about close to, to 57 centimeters now. So only 57 centimeters. Okay. Pretty close to 58. All right, ready? Okay. And 30 degrees, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.1.
15.1. Okay. Throw 20 grams on here. 20 grams. Another thing to keep in mind at this point is, like, once I start getting really small weights, like 20 grams, and we're going to do 10 here, okay, do you think the mass of the string is actually no longer insignificant compared to the mass? Yeah, that might throw things off too. You maybe make the effective length just a little shorter, but I'm going to keep it in the back of your mind. Okay, so 20 grams. Okay, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
14.8.
14.8, right. And, oh, actually this one's keeping its angle pretty good. It's still swinging pretty close to 30 degrees, so. You said 14.8? Okay. Okay, and then, interesting. So the larger weights are actually losing their angle a bit, but the smaller weights are actually able to keep their angle not too bad. Right, and then, let's see, find the little 10-gram guy, Right. Right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
14.9.
14.9.
We do want this before where it's in the
Oh, yeah, we're about to change angles. Yeah, so that'll be the next experiment. Now, yeah, you guys haven't written anything in your table yet, right? Or if you have, that's all right, but this isn't the one that I really care about so much. Because you guys see how the times are pretty much the same all the way down? Okay. So looks like the time per period, I'll have to just divide by 10, right? So 1.50, 1.51, 1.54, 1.54, 1.51, 1.48, 1.49, something like that, right? So there's the individual swing times. Okay. Sure this is on camera for you guys. Okay. All right. So a lot of you guys hypothesized this. I asked you guys before we started how should the mass affect things, and most of you guys said it should make no difference at all. And it looks like you're exactly right. Okay. Right. There's a little bit of variability in the length as we change out the masses, but I'm going to switch over, like present screen to share. Oh, well, not ready for that guy yet. Okay. We want to do this one right here. Block of two guys. We're on the graphs. So time versus mass. Right, so the times, let me grab this here. Or no, the masses went 100 grams, 200 grams, 500, 1,000, 50, 20, and 10. And the time periods went 1.5, 1.51, 1.54, 1.54, 1.51, 1.48, 1.49. Right. Now, I do want you guys to make the graph for this. So do you guys see right below the table, there's a graph that says T versus M? You guys see that? Okay. Hey, that's that graph on the projection. So go ahead and copy that down. I know it's a real tiny graph because this is not the most important one, but you know, right? So put time on the vertical axis. Make sure you scale it up to, well, about 1.5 seconds, right? So 1.0, 1.5, okay? And then the masses scale up to 1,000 grams. Pretty close there. Mass in grams, time in seconds. Oh, okay. What's this on the chat? Are you supposed to write this down? Yeah. So copy the graph. Yeah. So everybody's copying that graph right now, right? So time versus mass. Okay. No. Right, so of course this is pretty flat line, right? And you guys remember the basic graph relationships that I've thrown at you guys? I'll sketch this out real fast. Okay. So, you guys remember there could be no relationship where the relationship between two variables is one of these guys. There's no relationship between y and x. There could be a direct relationship, which is like linear. Right? There could be an inverse relationship. One variable gets big, the other gets small, vice versa. Right? You could have like a power relationship, like a piece of a parabola. Right? You could have a root relationship, which is like the same thing. You swap the axes. Right? Now, obviously, those aren't the only graph relationships, but those are some really common ones we see in this class. In this case, we got like no relationship. Right? So it doesn't matter what the mass is. Right, you guys ready to move on to the next variable? Right. How does the angle change things? Right. Now, this one also do not write down any data. Right. I'll keep track of the data though. Right. I'll have you guys make the graph at the end, but hang tight. Okay. So I'm going to keep the mass at 100 grams all the way down. Go back to what we started with. Don't write any of this. Okay. I'm going to keep the length locked in at 58 centimeters all the way down. Okay. But let's change out the angle. Let's go 10, 20, 30, 40, 50, 60, and let's jump this last one up to 90, see what happens. Okay, something like that. Okay. All right, you guys ready for this? Okay, so go back to the original 100-gram guy. We just confirmed this is at 58 centimeters. And yeah, it's 58. Right, so 58 centimeters, so we're all good there. Okay. Okay, so what I'm going to do is just change the starting angle. Right, you ready, Morgan, with the stopwatch? All right. So from 10 degrees. Okay, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.96. All right. We got 14.96. Let's bump this up to 20 degrees. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.95. Wait, think here. Let's take up to 30 degrees. I guess this one we technically have already, but let's just grab it again. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 15.2 is 1.52. Take this up to 40 degrees. I haven't really changed so much so far. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.4. Okay. All right. Take it up to 50 degrees. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.6. Yeah. How the angle's doing too. Right now it's showing about 35 or 40 degrees, somewhere there, so it's lost a little angle. Take it all the way up to 60. 60 degrees. Ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.7. See how the angle's doing. We're at it's about 50 right now. 15.7. Right. Let's take it all the way up to 90, which would be like horizontal, start horizontal. what happens. Ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 16.9. Right. And right now the angle is reading about 65, just in case you're curious about that. It said 16.9. All right. Okay. So this one I did not want you to write down yet either, because well, let's see what's going to happen here. Let me take this and pop this into Excel. Oh, I've been sharing my screen the whole time. Oops. All right, that's all right. Okay, so the angles went 10, 20, 30, 40, 50, 60, we did 90. There's times where 5, 2, 4, 6, 7, 10. Huh. All right. Do go ahead and write that graph though. Right. So you see time versus angle graph. Okay. So scale the vertical axis as time in seconds, and the horizontal axis is the angle in degrees. 20, 30, 40, 50, 60, 70, 80. All right. What do you guys think about that one? Yeah, Kevin, what are you thinking?
I think there's still no relation, and the difference between the angle and the time is just due to air resistance and the fact that the base was moving with the larger angle.
Okay. Yeah, I'm thinking of maybe something similar to that. So you guys think there's it's probably a constant relationship, like no relationship between two variables still. Yeah. So pretty constant graph. And it does have a little bit of upward drift, and Kevin was speculating some reasons why. He's watching that pendulum was not perfectly steady. It was bouncing back and forth a little bit. Maybe air drag, possibly. You know what else? And this is just one of my guesses. Is you guys see? How far can I move this camera? That this pendulum swinging is not actually from a single point. It's actually wound around this post has a pretty good diameter, right? Maybe about a centimeter. Okay? So as it swings back and forth, I bet when it's on this side, maybe the effective length of the pendulum is a little bit longer than when it's on this side. And just the time you get, it changes by about a centimeter, right? Up to the diameter that makes it sound about. Right? So that would be my speculation as to why maybe it curves up a little bit, maybe. I don't know. But we've got two variables down there. It looks like they both basically made no difference at all. So let's bring in length. Right now, here's where I do want you guys to write in the table. So if you missed that detail before, you've got this table filled out, then that's all right. But or if you don't have this table filled out at all yet, then that's what I want you to do. So let's keep the mass. Yeah, let's keep the mass at 100 grams because that's what's on there. I'll keep the starting angle locked in at 30 degrees. Try to keep it pretty close to 30 degrees all the way down. But the length, whoops, gotta switch my projection for you guys in class. All right. Alright, so this will be controlled, this will be controlled, but this time I'm going to take the length, make the length the independent variable. Of course, I want the time to be the dependent variable. I'll record this number as we're going along. Right, we'll see what happens. Okay. Oh, I remember what else I wanted to say. I forgot this detail. Okay. Let's go back to the one where the angle is changing. Okay. I'm going to give you guys a full historical detail on this. What we just did, where we're leaving the mass controlled and treating the angle as the independent variable, leaving the length controlled. Okay. This was one of the very first science experiments that was ever done, actually by Galileo Galilei. He was in a church and he was watching something swing from the ceiling. It was basic pendulum. And he did notice that after some time that pendulum was losing energy, to say that its angle from the vertical was getting less and less. He noticed that, just like you guys saw, right? That over so many swings, the signal was not exactly consistent. Right? And he used his pulse as a rudimentary timer, and he noticed that it didn't matter what angle it was swinging at. It took pretty consistently at the same time to swing back and forth. Yeah, that was one of the very first science experiments that was ever done. We just did. Okay? So let's go on and figure out, how does the length of this thing affect the time? I mean, someone's got to affect time period, I would think, right? Otherwise, all pendulums should swing at the same time period, and that wouldn't make any sense. So I hope length has some kind of effect, because we're kind of running out of variables. All right, so let's start this. Maybe I'll start this thing really long and just make it shorter as we go on. All right, got a pretty good length pendulum right there. So this guy is at 74. Right, we're looking at 74 centimeters. 74 centimeters. Gonna pull this back to, okay, remember this guy's 100 grams. I'm gonna pull this back to 30 degrees. Right, ready, Morgan? Okay. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17.06. Yeah. Ooh, its angle is kept pretty good too. So 17.0. Hey, we're getting something that's not the same time as it's been all along. Huh. Maybe we finally found a variable that actually matters. Make this a little shorter. Alright, so what's this length now? This length is 63. Alright, so 63 centimeters. Alright, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.96. See what? Okay. Huh. All right, make this a bit shorter. Right here. And so the reading, the length is now 50. 50. Oh, is that right? Yeah, 50. About 50 centimeters. 5 centimeters. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.01. Shorten this some more. Okay, now we're looking at, see, I'm going from the center mass of this weight up to the top point, 38, looking at 38 centimeters. Okay. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
12.23.
12.22. And so this one is 26 centimeters. 26. All right, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.81. It's got shorter. 1. This is 13 centimeters. Right, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.15. All right. How sure I can get this thing? Well, yep. Run out of length at some point. See what we got here. What is this? It's about the shortest pendulum I can create here. 9 centimeters. It gets ready to do 9 centimeters. Gonna go fast. Right. Yeah, like most of this pendulum is it's just the weight itself, right? It's like this little Captain Hook going on here. Okay, ready? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.85. Second, 0.5, like that. All right. So you guys at home, hopefully we're able to follow that and record that table, but there you go. There's the visual on that at home. Okay. Okay, we definitely have something interesting going on here. I see as the length is getting shorter and shorter, the time period is also getting shorter and shorter. A lot of you guys did hypothesize that before we started. Right? I wonder what this time versus length graph is going to look like. That's one we're about to do, right? This big one right here. So put time in seconds here, put length in centimeters here. Right? And yeah, let's try this out. So I'm going to switch over to present screen 2, share, have Excel make a really nice looking graph for us. And then, yeah, we'll figure out what to do from here. So the length went 24, 63, these are of course in centimeters. Okay. And the time periods went 1, like that. Yeah, that's what that should look like. So you guys copied that down, well, I'm copying it down. What kind of curve do you guys think that is? Is that a direct relationship? No, it's not direct. So if you drew a straight line through them, first of all, the points don't really look like a straight line. But even if they were, there would be a huge intercept here, which doesn't really make a whole lot of sense. Okay? I bet it's some kind of root relationship, doesn't it? Doesn't it look like a root? Okay? Now here's where you have to speculate. Say, is this a square root or a cube root or a fourth root or maybe something weird, like maybe it has a power of like 0.7 or something crazy. We don't really know, but I'm going to take a guess. Maybe it's a square root curve. Okay? And if it is a square root curve, then we could linearize this thing. You guys remember linearization? Okay. We do a quick review with you guys, assuming this is a square root curve. Okay. Did I mention at the beginning of class that there's like two like categories of labs that we do in this class? I forget if I mentioned this, but one category of lab is like what we have here, where we're cavemen, we don't understand how physics works, and then we just try a bunch of stuff and do all these experiments and we figure stuff out, exactly what we just did. The way that AP asks you lab style questions is more the other category of labs, which is that you know how physics works, you know what the equations are, and you're supposed to maybe chase down some kind of constants or something like that. And a lot of the times that involves linearization, which is what we're about to do here. So if I suspect that, say, on the time versus length graph, if I got, I mean, the line of best fit would be, the curve of best fit is something looks like that, right? If I suspect that time is proportional to the square root of length, okay, then what can I do with that? If I want an equation time is equal to something, then I have some kind of constant here. Here's another way to say this: time is equal to some constant times the square root of length, maybe something like that. But I wonder what this constant is. Right? Well, there's two ways that you can linearize this graph, and I gave you guys two graphs in the back, but just pick one of these. You guys will have to do both of these. Okay. So either do see what you could do is if I square both sides, couldn't this look like this? Like time squared should be proportional to just plain L, something like that. Okay. So whether you do time versus the square root of L, or if you do like this top one, time squared versus L, right? If we were correct to say this is a square root relationship, then both of these should line up in a straight line, right? Now, of course, they'll have different slopes with completely different units, right? But they should line up in a straight line. Let's see. So I'm going to flip over back to Excel. I'm going to let Excel go ahead and run this for us. So just scroll up just so you guys can see the tables. So we have the square root of L and then T, right? versus down here I have L and then T squared. So I'm gonna have Excel do both of the graphs. Right? Hey, look at that. They both line up in really nice straight lines, don't they? Yeah, look at that. Nice straight line. Oh, we'll zoom out. So pick your favorite graph. Whoops. Pick either the, what's it doing this? Okay. Either the top one or the bottom one. Pick your favorite graph and draw that one. Okay. And I'll do one of them while you guys are doing one of them also. Hey, you guys got one of those graphs drawn? Alright. I remember what I was gonna do. I was gonna find a line that best fit. So I copied the first one down. Let me go add trend line, display equation, and here, add trend line, display equation. Okay. I mean, you guys have done enough AP classroom questions that you guys know that they do like to ask, like, let's say students are trying to discover, blah, 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 some property. They do some experiment. Can they figure out like some number? And you're supposed to say, well, I want to put maybe like time versus the square root of length, some variable versus some other manipulated variable, and then like take the slope of a line, something like that. Like, this is like very in tune with that kind of thinking. Right? And blow these up, equations a little bit bigger. Right? So whichever one you did, I have an equation here. You guys have the y-intercept of each one is pretty much 0. Subtracting a tiny decimal in each one, but the lines themselves looks like they go pretty much to the origin. Okay? So I do care about the slope though. You guys see two different slope values with, of course, different units attached to them. Okay? Let's say take a look at this top one because that's the graph that I copied down. Right? This 0.2035 number, I wonder that's like theoretically what it should have been. Right? Because it looks like the only variable that made any difference was time, right? Okay. Let's flip back over to this page. Okay. Oh, yeah. Let's finish off this equation here. See what it says? Therefore, time is proportional to. Okay. That's another proportional sign. Okay. So, how does it relate to mass? It doesn't. How does it relate to the angle? It doesn't. How does it relate to length? Time is proportional to the square root of length. Okay? So you could say time is proportional to the square root of length. If you wanted to, like if this were a multiple choice option, you could have time squared is proportional to length. That would also be equally valid, right? Something like that. Well, let me play out this top one. If time is proportional to the square root of length, then maybe more specifically, I could say time is equal to some constant times the square root of length. Couldn't I say that? That would be true too, right? This is the whole answer to the lab, by the way. It's just something like that. Right? But I wonder what that constant is. Well, we have a number for that constant because we just got it empirically. Right? We got it from this Excel stuff. Right? I wonder how close this lines up with what it theoretically should have been. So here's where I'm going to give you guys an equation. Actually, instead of just giving it to you, instead of writing it down, I should point it out. One of the pages I handed you guys was this page. This is some very fundamental problems for what we're about to be looking at. Okay? You see how one of the equations right here says pendulums, time period is equal to 2 pi times the square root of L over G. Hey, I bet that's what we just did, isn't it? Right? What's the time period of a pendulum? Or time period swing back and forth once. Okay? Well, they've got square root relationship. You know what else they have? They have something to do with gravity. Now that's a variable that we did not touch in this lab. I mean, it'd be kind of hard to, right? Kind of hard to change the gravity field within a high school classroom. Okay? But can you guys do a thought experiment? What if we took the whole experiment that we just did and we take it up to the moon, right? And on the moon, of course, gravity is very weak. Do you think that the pendulum on the moon would swing very quickly or very slowly? What do you guys think? Yeah, very slowly. Does it make sense? Right? And let's see if this checks out here. I'm just going to take this and write it down. Get the papers in order here. Put this side here. These back up here. Yeah. All right. So we've got time period is equal to 2 pi times the square root of the length of the pendulum divided by the gravity field. At least that's the textbook answer to the lab we just did. Okay? So if we go to the moon, where gravity is very weak, wouldn't we be dividing by very small numbers compared to Earth? Okay. Earth, this number is 9.8. On the moon, it's like, I think 1.6, something like that. Okay? So, meters per second squared. So anyway, if this number is getting smaller and smaller, the overall fraction is blowing up bigger, 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 which means that, it takes more time to swing back and forth. Yeah, totally makes sense, right? So I wonder how close we got this. Rewrite this a little bit. Should be 2 pi divided by the square root of g, all times the square root of L. That's saying the same thing, isn't it? Okay. But the reason I wrote it like this is because when this, isn't that like the slope of the line that we just did? Well, one of the two graphs. Okay. Let me flip back and show you guys. Present, screen, 2, share. Right. If you went the other way and you did the other graph, then that's fine. Right. These are both referring to the same set of data anyway. But I'm specifically looking at this top graph. Right. Take a look at that slope. 0.2035. You guys see that? 0.2035? Right? That's what all that stuff is equal to. Let me come back over here. Right. So 0.2035. Also that number has units. Time is equal to something times the square root of L. This is our, here, let's say this is our empirical data. Right. Guys, what are the units on this number, this 0.20 number? Who could figure that out? I mean, for example, it's not kilograms, obviously, because you couldn't go from length to time period through kilograms. That would make no sense. Okay? Who can tell me? What's the unit? Yeah, Jared, what are you thinking? Close, right?
Seconds per meter? I don't know.
Seconds per meter is actually a little bit closer, right? Because guys, if we're plugging in some length unit, that would be like meters or centimeters. Actually, we did centimeters, didn't we? Centimeters. So has something to do with centimeters. We have to divide that out and multiply in something so that we get some number of seconds. Wouldn't that be true? Right? So we have to divide out the centimeters, but it's being square rooted, so it's really like square root centimeters. Right? And then we need to multiply in seconds so that we get some number of seconds, right? Now this is a really weird unit. If you went the other graph, you want time squared proportional to length, then you would have square seconds per centimeter. But I went this other way, so I've got seconds per square root of centimeters. Really weird unit, but that's how, right? For example, what if we came up with some other length pendulum? Like, what if we came up with, I want this pendulum to be 148 centimeters long. I wonder how much time it's going to take back and forth. Well, we have the predictive powers of science. Right? Now we can say, well, we know I'm plugging 148 centimeters here. I'll multiply by this empirical number. This centimeters cancel out. Right? The seconds come back into play, and now I can tell you a pretty good prediction of how many seconds it's going to take. Okay? So I wonder, this number and this number, I wonder if these are the same thing. Okay? You guys want to see? Let's try it out. Let's do 2 pi divided by, now g, or actually square root of g, right? Square root of, right? Now if I want to compare these numbers directly, don't I have to have the centimeter version? Right? What number should g be in terms of centimeters? Yeah, good call. 980 centimeters per second squared, wouldn't it? Isn't that true? Right. You guys see how the centimeters is obviously being square rooted just like here? And the seconds, well, it's being squared and square rooted, so those cancel out. And it's also within a fraction, so it flips back up on top. It'd give you seconds, wouldn't it? Okay. So I wonder how the number plays out. Let's see. I hope it's really close to this number. Let's see how close it is to this number. What is 2 pi divided by the square root of 980 centimeters per second squared? That gives me 0.2007. That's this weird unit. Hey, look at this. This is, of course, the textbook number. Textbook. Okay. Oh, yeah, so Morgan did a really good job with that stopwatch because that's extremely close to what should have been. You see that? It's like the same thing. Okay, so good job there. Okay. Yeah. Right. Any questions about that lab? Okay. Let's see. Stop sharing my screen. Right. Right. So, okay, you guys good so far? Okay. So hang on to that for just the rest of the class period. Now I know on the, if you're in class, then on the back I printed like a lab write-up. Don't worry about the lab write-up. I don't really change my mind on that. Okay. Probably get to a lab write-up next week, but not for this one. Okay. Let me go back to presenting my screen, because here's where I want to make a connection to very similar phenomenon. Right. Need to introduce you guys. Oh, well, no, too fast. No. Some new ideas. Let me flip back to projection. Never mind on that. Okay. So you guys know what time period is. Okay. Time. So capital T, time period. Right. So for anything that's oscillating, right, like a pendulum oscillates, just you could call it simple harmonic motion, just harmonic motion, just back and forth over and over. Right? So this is the time to cycle completely once. Okay? And you can measure this in some number of seconds. Okay, so no problem there, right? Okay. There's a related idea. There's something called frequency. And well, we're just going to start with this, lowercase f. It's going to represent frequency. Some textbooks use the Greek letter, I think it's called nu, I think. It looks kind of like a stylized V, but we're just going to use F. Right? And this is the reciprocal of that. Actually, frequency and time period are reciprocals of each other. Okay? So it's like how frequently does something happen? So you take the reciprocal of the time period, right? And you can measure this in some number of what are called hertz, right? But, okay, so what the heck is a hertz? Right? Well, if you look at this sort of definition of frequency, one of the time period, you can probably figure it out pretty quickly, because if time is in seconds, wouldn't hertz be some number of like cycles per second? Or the metric unit would be like 1/seconds. Okay, guess that? Okay. Right, so so if it says something like 4 hertz, that would be like 4 cycles per second, which should the metric unit is just like 4 times 1/seconds. Okay. You guys remember last few weeks how radians was sometimes one of those sort of invisible units, right? We're working with it, swapping back and forth between rotational and linear motion, and sometimes radians, kind of popped in or disappeared. Similar idea here with cycles, like cycles per second. The metric unit just shows 1/seconds, like big hertz. Okay. Okay, so we flip back to computer, present screen to share. Okay. and my demos. Okay. So yeah, so let's start off with a frequency demo. You guys hear 1 beat per second? So you can call it 1 hertz, right? 1 beat per second, 1 hertz. Ooh. You guys hear 2 beats per second? That's 2 hertz. There's 4 hertz. What's that? Oh, yeah. Yeah, so that's what I got here is like 8 hertz. You guys hear like 8 beats per second, 8 cycles per second. Okay. So I could keep pumping it up, right? Now, do you think at some point your brain would probably not be able to distinguish the beats anymore? And so probably kind of like a hum, like, right? And then if I kept turning up, probably sound like a pitch that was like winding up. Okay. That's actually how you can define musical notes. Like one of the notes on pianos, it's like one of the A notes is defined as 440 hertz. Right? So if your brain could perceive it, it sounds kind of like beats like that, right? Or if I had like 440 beats, right, every single second, it would sound a lot like an A note, right, from like some musical instrument, something like that. Okay. Next demo. Okay. So here's some harmonic motion too, except that this is definitely not a pendulum, right? Although it has very similar motion. I'll point out to you guys too. Okay. So looks like we have some red mass, this block, on a spring. Ooh, we're introducing a spring. Huh. Okay. And see how it's oscillating back and forth? Right? Just like the pendulum was oscillating back and forth. Okay. There's some time period associated with it. Okay. So it's going from the top back to the top. So there's cycle, 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 right? Looks like every single cycle is taking just over a second, maybe about something like that. Huh. It just cycles over and over, right? Look at its displacement or speed. Actually, let's focus on speed, right? So see how it's going like fast, slow, fast, slow, fast, slow, fast, slow. It looks like it's going really fast through the middle point, and then it kind of slows down near the top and bottom, right, as it's turning around. Huh, that's interesting. Right, so how can we put this all together? Right? If you look at the circle to the right, see the blue circle to the right? Right? There's a connection between the animation on the left and the animation on the right. You see a green dot going around on the right side? Kind of hard to tell, but you guys can see a green dot going around. Now that green dot is going around at a constant speed. Notice I did not say constant velocity. Imagine we're up in a helicopter, we're looking down on a racetrack, and there's a green car that's just going around, and its speedometer is just pointed at the same number over and over. So same speed, but he's always turning to the left, right? There's a centrifugal force on this guy, but the speed is the same. Right? Now look at the elevations of these 2 green dots. There's one in the middle of this red block, and there's one that's going around this racetrack. Right? Notice they have the same y-coordinate at the same times. So if I were to take a meter stick and rest it on these 2 green dots, see how the meter stick would stay level, but it would just kind of bob up and down with the block? Yeah. Huh. That is telling about the vertical motion of this red block. Right? The fact that it has the same y-coordinate as this green race car moving at constant speed around a circular track. Right? If I were to graph the position versus time of this red block, or maybe that green dot within the red block, right? What kind of graph would that be? I bet a lot of you guys know where this is headed. What kind of graph? Position versus time. Like a wave? Yeah. All right. You guys thinking maybe like a sine or a cosine maybe looking wave? Something like that? Right. Let's go back to projection here. Yeah, tangent graphs are especially fun, right? But no, we're just going to be using we're about to hit sine and cosine here, right? But what you may notice, see, right? See, remember I was pointing this out for pendulums, 2 pi times the square root of L over G, right? Is the time period, right? Right below it, it tells you what it is for springs. It's a very similar looking formula, right? So, whereas for a pendulum, it was 2 pi times the square root of length of the pendulum divided by gravity field, right? time period for that, well, I'll say spring, right? But like a mass on the end of a spring, the animation you guys just saw, right, goes like this: 2 pi times the square root of. So far it's looking the same, right? Except instead of the length of the pendulum divided by gravity, because it's obviously not a pendulum anymore, it's the mass of the block divided by the spring constant. Ooh, that's the animation that you guys just saw, right? In fact, if you memorize one of those formulas, then you could probably very quickly remember what the other one is, right? Or you know what? You don't even have to memorize them necessarily. These are equations on the AP equation page. Let me dig that up real fast. Just point them out to you. Right. Here they are. Okay. You see these two right here? Time period for a spring, time period for a pendulum. There you go. Right. There they are on AP equations. Right. Okay, good. Okay. Now let's make those graphs that I was referring to. Right. Remember, we're looking at the green dot, and its y-coordinate was the same as that green dot moving in a circle, constant speed, all that stuff. Okay. So we're over here. Okay. I want to make a set of 3 graphs for a mass on the end of a spring. Right. So that animation you guys just saw, it is like a spring and a mass, and it's just kind of bobbing up and down, boing, boing, boing. Or maybe it's horizontal. Okay. So you guys remember tossing balls off cliffs, and we made these 3 graphs of distance versus time, velocity versus time, acceleration versus time? That's exactly the same 3 graphs we're making here. Well, of course, they're going to look completely different, but same sets of axes. Okay. So I'm going to put time in seconds on each one of these. Okay. And then let's look at displacement, like vertical displacement, if it's bobbing up and down, maybe some number of meters. Okay. I'm interested in how fast is it going, like meters per second. And I'm also interested in acceleration, like meters per second squared. If we were to dig that far into it, I wonder what these graphs are going to look like. Okay. Now, maybe this the system like starts at rest something, and maybe you pull it back and let it go. It starts wow, wow, wow. Right? Really, I'm pulling it back from the equilibrium position. So, and if I were drawing, I'm about to do something kind of funny with this first graph. Strictly speaking, I should actually, from time to 0, have it not emerging from the origin, because I need to pull this block back to set it in motion. Right? But let's say that I start keeping time right when it's crossing through the origin point. Right? You guys know spring has some natural length where it's neither stretched nor compressed, something like that, right? So yeah, go from there. Okay? Now, the fact that you guys saw that green dot had the same motion as, well, you saw its motion compared to the dot around the circle. Okay? You guys said that should be like either sine or cosine. Okay? So if I start from the origin like that, actually would make a like a sine curve. And this could just keep going on forever, right? Okay. So a very simple graph might look something like this. Displacement as a function of time is equal to sine of however much time has passed. Okay. Now, obviously, this equation gets more involved, but just a very fundamental relationship might be something like that, right? You pop in time has something to do with the sine relationship. It can tell you where it is, how high up or down it is, right? Okay. Okay. All right. Now, what about its speed? Because now this is something that we were looking at too with that animation. It was speeding up and slowing down, like it wasn't constant speed all the way across. So I wonder how we're gonna get speed from this. Does anybody know? Yeah, Lily, what are you thinking? It is cosine. Yeah, true. Yeah. How do you know that? Yeah, she's saying derivative of sine is cosine. Right? How many guys are taking calculus? How many guys take? Ooh, yeah, bunch of guys, right? Not everybody, and that's okay if you aren't. But you might remember back when we were throwing balls off cliffs. Remember how velocity is the rate change of displacement, right? And in calculus, the term for that is called derivative, right? So in the graphical relationship, it has to do with slopes, right? Look at the slopes of these things. See how the slope starts off really steep, right? And then here the slope goes to 0. Then here the slope is like negative pretty steep, right? And then by the time it gets to this point, 0 again, and then it just cycles around over and over, right? So, maybe I want to line up some points here. I'm interested in maybe something to do with this peak point. I'm interested in this 0 point right here. What's going on with those other graphs? I'm interested in this trough right here. Ooh, I hope all these lines are parallel. Right, I'm interested in this point. I'm interested in this point. At some point, this just starts cycling. Okay. Right. Let me make points of comparison. Right. See where we're saying if you take the slopes of x versus t, that gives you the v versus t graph, and eventually we're going to head on down to the same relationship here. The slopes of the v versus t tells you a versus t, right? Because it's like a rate change. Okay? So let's see. I see at this point here, at this very top, see how there's 0 slope? There's 0 rate change right at the very top. So I'm going to say it's 0 velocity, right, for the coordinate. The slopes of this graph tell you the coordinates of this graph. And then later on, the slopes of this graph are going to tell me the coordinates of this graph. Okay? I also see a 0 point right here, this trough, 0 point this peak, 0 point this trough. So that's going to be cyclical. Okay? And then, let's see, it looks like the slope was extremely positive here, extremely negative here. Sorry, right here, extremely negative right here. Right? And then that kind of cycles back and forth, something like this. Okay? And yeah, if you connect the dots, it does end up being also sinusoidal. Oh, that's the name of these graph relationships, by the way. Right. Did I do that right? Yeah, like this, and they could just keep going on. Okay. Yeah, and yeah, this could be, yeah, just a very fundamental example. Exactly what Lily said. This could be a cosine, very basic graph. Okay. I'm gonna write down that word sinusoidal. Sinusoidal. Because I talked about some basic graph relationships that we could have. Somewhere I wrote it down. Okay, you guys remember constant no relationship or direct relationship or square root, inverse. Right? Here's a new type. Right? It's like the sinusoidal, like anything that like oscillates back and forth. Okay? Let's try this again. How can we go from velocity to acceleration? Maybe take some slopes again, right? Now here the slopes is 0 there, right? So we've got 0 slope, means acceleration is going to be 0 coordinate. Right, so that could be at all those points. Hey, that looks a lot like a displacement. It was also 0 displacement means 0 acceleration. Right? Think about how that could be consistent even before I draw this curve. Right? Guys, if the block is going through the point of 0 displacement for a spring, maybe it's even more straightforward if I think about this being horizontal, right? Being like frictionless surface going back and forth horizontal. Right? When it's going through the point where the spring had its natural length, isn't there a 0 force from the spring? If there's 0 force, wouldn't there be 0 acceleration going through Newton's second law of motion? Kind of makes sense, doesn't it? Right? Is this graph I'm about to draw going to look exactly like the first graph, or is it going to look a little different? Oh, what are you thinking? Negative. Oh, yeah. Yeah, so Eric and Lily are both saying it's going to be like, it's going to look like the first one, but upside down. Negative, right? Wouldn't that be true? Because look at this point. Got a really negative slope. It's a really negative coordinate. Really positive slope. Really positive coordinate. Hey, it's like this, isn't it? And go, looks a lot like the first one, but upside down. So this might be like acceleration as a function of time is like maybe a negative sign. Something like that, right? And you could just repeat this forever. Could you just keep taking derivatives forever, find rate changes? Okay? That's something else that's different from what we normally do in this class. Well, we normally stop at acceleration and say like almost all the time in this class, acceleration is constant, right? Very rarely is it ever not constant. And this is one of those exceptions, right? Do you guys remember, I think I told you guys last week what the rate change of acceleration is? What's the rate change of acceleration? There's a name for it. It starts with a J. Jerk. Yeah, it's called jerk, right? AP doesn't ever mention jerk, and you don't have to worry about it. But yeah, if you win another derivative, take another rate change, you can get a jerk graph that also oscillate like this, right? This is an interesting motion. Okay, you guys good so far? Okay, so finally, last few minutes here, I want to throw you guys some basic graph terminology, or sorry, wave terminology. All right. So you have some wave. Right? Maybe this wave is in motion. Maybe it has like a velocity, possibly. Right? I see some distance between like crests. I see maybe there's some time period associated with that motion. Right? I wonder what these things are going to be. Okay. So the shortest fundamental piece that you can take and just like copy paste it next to, see if I cut this part out and I copy paste it next to itself, makes a nice smooth wave. And that's the smallest piece I can do that with, couldn't it be? See what's like crest to crest? This is called a crest. So crest to crest, this is called a trough. Okay. This is called wavelength, and it's represented with Greek letter lambda. Wavelength. Okay. Now, it doesn't have to be crest to crest. It could be from this node, it's called a node, to this node. Sometimes crest and troughs are called like antinodes. Antinode. You ever see that word? Okay. Especially if it's a standing wave. We'll talk about this more tomorrow, right? But hey, see that full like S shape? Well, kind of the backwards S, I guess. Full S shape. Right? That could also be a small unit that could you copy paste that next to itself. Okay. Ooh, guys, how many wavelengths did I draw here? You see one there and one there, like two full S shapes. I see two full wavelengths. You guys see two wavelengths? 1, 2, right? If this is a motion, I bet it has some speed, right? Do you guys think that? Oh, I'll just write this down. I'll give it to you. But I want you guys to think about this critically. Take a look at this formula right here. Could you guys imagine if this thing was in motion? It's like moving left to right. These crests. Let's say you have a checkpoint, like a checkpoint right here, right? And you're watching these crests move left to right, maybe like an ocean wave, right? Do you think maybe there could be like some T time period between these crests, like crest, 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 right? And I told you guys earlier, remember how time period and frequency are reciprocals of each other? So you can go both ways with this. Like that's a valid formula, that's a valid formula. Either way you go with it, right? That's also in your AP equation make, right? Okay, so there's some time period associated with like blip, 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 past the checkpoint, right? And if you take the reciprocal of that, you'll get like some frequency, like how frequently these crests are hitting, right? And take a look at this formula right here. So if you know the distance between these crest to crest, that's called wavelength. That could be in meters, couldn't it? And you also know how frequently, blip, 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 reciprocal of the time period. Couldn't that be like 1 over seconds? Right? So if it was like 2 hertz, it would be like blip, 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 blip. If it was like 4 hertz, it'd be like blip, 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 blip. That'd be like 4 hertz, right? So many cycles per second. Hey, look at this. Meters per second. That could give you a speed. Like meters per second, right? Guess that too? Right? So that's a very important wave formula that we're going to be using over next week. What else we got? Maybe something called amplitude. Call it capital A. Right? From this middle nodal line up to the crest. Right? This is called amplitude. Okay. All right. So guess what? That will get you started for what we got coming up. So before you guys walk out of class today, drop your lab in the grade tray. Make sure you guys got one data table, all the graphs, and that answer at the end. Don't worry about the write-up on back. So throw that in the grade tray. Everybody at home, of course, upload your lab to Focus. And yeah, we will continue this oscillation waves adventure tomorrow.
Okay.